Welcome, GOBC Chem 114. We're diving into chapter 15. We're talking about lipids, and we're going to go into section 15.4. We're going to learn a little bit more about the properties, so it's just growing on what we just discussed earlier. And we started talking about triacylglycerols, where we take a trihydroxy alcohol and we react it with three ester molecules, or excuse me, we form three ester bonds and we react the trihydroxy alcohol with three fatty acids which have carboxylic acid. So all we're doing is talking more about esters, but with molecules that have multiple ester bonds in that same molecule, right? We saw that. Glycerol reacts with, say, stearic acid. Stearic acid has 16 carbons. It's completely saturated. It has no double bonds, okay? We learned about oleic acid. For example, oleic acid, it too has 18 carbons. Stearic acid has 18 carbons. It's a fatty acid. Oleic acid has 18 carbons, but it has a double bond. It has a point of saturation at the double bond at carbon 9. We saw that. We've seen that. So bear with me. Okay, so soft margarines are often sort of hydrogenated because if they were unsaturated and if they had a lot of double bonds, it would be oil and not a solid. So margarines can be partially hydrogenated where you add hydrogens to get rid of unsaturation in those fatty acid chains, and therefore you make it more solid. You can take vegetable oil, you can hydrogenate it, get rid of the double bonds, turn everything into a single bond. Remember, single bonds, sigma bonds, right? Alkenes versus alkanes. You turn it into more, you hydrogenate a vegetable oil, you turn it in from more like an alkene to an alkane. Alkene to alkane when you're hydrogenating. Uh, so let's see where we can go with this here. Um, let's talk about hydrogenation, hydrolysis, and saponification. We already seen what hydrogenation can do. We make a solid. So moving forward, if how do we do this? How do we do this hydrogenation? Well, this is kind of repetitive, right? We've seen this before, but now we're talking about these triacylglycerols, right? That have three fatty acids attached to a glycerol molecule. And well, it's the same thing. We have the double bond that's part of the larger molecule or the complex of that molecule. We add H2 gas. We then have nickel as a metal catalyst, and we're able to add two hydrogens after we bubble the gas in, and it kind of attracts to nickel, and all these things kind of that's how it happens is mechanistic, and we're not really showing mechanisms in this course, but you can learn more about that if you're interested. But you get rid of that double bond. The alkene becomes an alkane. It goes from unsaturated to what? To saturated. Now moving on, let's do some more chemistry. Let's do it to a molecule called glycerol trioleate, right? So it has 7, 8, 9, 16, 17, 18 carbons. Oleic acid is a lot like stearic acid, but it has 18 carbons, but oleic acid has a double bond in it, right? So if we go and we hydrogenate this on all three of these extensions off of glycerol, we end up getting rid of that double bond in three different places on this molecule for effective in our reaction, and we turn it into glycerol tristearate. So it has a totally different name because we know oleic acid structure as an unsaturated, monounsaturated fatty acid, but when you have stearic acid and you form a ester bond with it, you're going to turn it into a stearate. So makes sense. Which one is going to be more flexible? Which molecule is more flexible, the reactant or the product? You should say that the reactant would have been more flexible. It has unsaturation. It has a kink. And this saturated molecule, which has been hydrogenated, is going to be less flexible and it's going to be more like a solid, right? Moving on, commercial hydrogenation. That is what they do. what we just saw is what they do in a lab, in a food operation. They hydrogenate to turn that liquid into more of a solid if that's going to be beneficial for their packaging and for the use by us humans, right? So liquid vegetable oil can undergo hydrogenation and it becomes a solid and it has a higher melting point, right? We don't think of that, but even our foods are part of what chemistry is all about, right? So, what products are obtained from the complete hydrogenation of glycerol triolate, which would have came from oleic acid, which would be 18 carbons. And since it's unsaturated, it has at least one double bond. It kinks it, it makes it liquid. But if we hydrogenate it, we're going to turn that alkene into an alkane, and we're going to turn it into into stearic acid or a stearate. Now, all we do is hydrogenation. Now, if we added sodium hydroxide, we might be able to, or water and acid, we might have been able to break the ester-like bond and got C. But in this case, it's going to be B. We're going to get glycerol tristearate, just as we've kind of seen from the previous slide. So this is kind of cool, chemistry in our foods. And moving on, we talk about unsaturated fatty acids. We know they tend to be oil-like and they have higher melting points than saturated, right? So unsaturated has a kink, it has a double bond. And when it's this way, it's a trans, or excuse me, when it's cis, as we see in this box, it's cis because the two largest groups attached to the double bond are on the same side. The hydrogens are on the other side, right? Remember how we add hydrogens when they're missing and how we use the line formula to save time. So make sure you understand that, or this can look like Greek. Nothing wrong with the Greeks, but can we read hieroglyphics or whatever, Egyptian maybe? But here we have a double bond, and guess what? It's trans. There's a hydrogen here and a hydrogen there, but the other carbons attached to the double bond are on opposite sides of each other. That makes it trans. It doesn't change very much about the order of the molecule. The molecule is still kind of ordered almost like if it was a saturated fatty acid, but it's still considered unsaturated because of this double bond. This is unsaturated. This is unsaturated. But this trans unit, this trans fatty acid here is probably has a lower, or excuse me, it probably has a higher melting point because it can stack better. It doesn't have a kink such as the cis group does. So that's a difference. That's going to play a role in whether something is more like an oil or something is more like a solid. And of these two, which one is more like an oil? The top one. It has this kink. It's not going to be able to pack and stack as well. But the trans doesn't do much difference to the overall structure as if it was saturated and the double bond was gone. It still kind of has almost the same order. During hydrogenation, double bonds are converted to single bonds. This is kind of review stuff. Some of them are going to be cis, but some of them may convert to the trans double bond, which is actually more stable. Remember, we talked about trans bonds with the groups further away from each other on opposite sides has less energy than a cis bond, which is going to be higher energy. It's going to be a little bit higher energy. And let me just draw this out very briefly. So this is the cis bond, and this is the trans bond, right? And this one is higher in energy, right? This one is higher in energy if we think about energy. And you're like, Dr. Pryor, why are we even talking about energy? What are you talking about? Because if you go further on, you're going to learn that everything is about energy. How we make these molecules depends on the energetics of the universe, which makes sense, right? I mean, why can we not run 100 miles without not getting tired, right? 100 miles without getting tired. Almost every human being on the planet would not be able to run 100 miles without getting tired, right? And that has to do with the rules of nature, how our bodies are made, how we store energy, how we can use energy, how fast we can use energy. There's all these interesting things to look at. Now, here it talks about trans fatty acids. they behave pretty much like saturated fatty acids, right? So they are unsaturated, but they're trans. And so they don't have that kink that cis double bonds have, which makes them more oil-like, right? It is also the same thing with LDL cholesterol and lower HDL cholesterol. Low density lipids or low density cholesterol is easy to get rid of out of our system without it clogging up our arteries and stuff. But when we have high density lipids or high density cholesterol, they compact together really tight and form solids and can clog up our cardiopulmonary systems, which we don't want, right? We want to live. And so we have this cis fatty acid. Maybe it's oleic acid. I don't know. But it has see how it's kinked? It is a cis fatty acid. But look at the trans one. It's still kind of, it doesn't have the extent of the kink. It's kind of the same. And we don't want that because it will have for one, it'll have a higher melting point. It'll be more solidified and it can pack together closer. If we have the cis fatty acid, it doesn't do that. So in the process of doing hydrogenation to this molecule, we can take the cis fatty acid, hydrogenate it with nickel, and we get our completely saturated molecule. But it may cause some side products. We may get a trans fatty acid, right? And that we don't want because it has to do with a lot of chemical things like isomerization and things that go on where this molecule is moving around during the process. And as a result, you just end up with some trans side product that is still unsaturated, but it has the properties of as if it was saturated, right? So an unsaturated molecule acting like a saturated molecule is when you have the trans double bond. In this case, you have everything saturated, you've gotten rid of the double bond, you've been effective, but of course now you're going to have a higher melting point. This is going to be more solid. They can pack together more appropriately, right? And therefore be packed together more densely. That's where you get HDL and LDL, high density, low density. That's what HDL and LDL mean. Low density is the good cholesterol, HD, high density, is the bad cholesterol. And so let's move on. Foods contain many of these trans fatty acids, including milk, eggs, and beef. And when they're trans, they still tend to have some uh, high density capacity. Remember, it's the cis that gives us the liquid form, that gives us the more liquefied form. And foods that contain trans fatty acids from hydrogenation processes include deep fried foods, breads, baked goods, cookies, crackers, chips, sticks, soft margarines, and vegetable shortening. Many of these things don't taste all that bad at all, like cookies and bread and crackers and all that good stuff. So it's not that this stuff is completely bad for us, it's just we have to be careful, right? So which of the following statements are true and which are false? So let's evaluate each one. There are more unsaturated fats in vegetable oils. And we should say, well, you saw from the chart, yeah, there's a lot of unsaturated fats in vegetable oils compared to, if we're comparing it to animal fat. So this is sort of a kind of open-ended question. That would confuse me because what are we comparing it to? Because we know some vegetable oils have saturated fats, right? But yes, this is primarily true. Vegetable oils have higher melting points than fats. Well, oils have lower melting points than fats. So this, in fact, B should be false because it's the opposite. Hydrogenation of oils, which we just saw, right? We saw hydrogenation where we add H2 across an alkene, converts cis double bonds to trans double bonds. That is true because that can possibly happen as a side reaction. It's definitely partially true. D, animal fats have more saturated fats. That's true too. So we know that they have more saturated fats from the chart and the analysis that we saw. So again, B is the only one that's false, that vegetable oils have higher melting points than fats. No, fats have higher melting points than vegetable oils. So let's move on. And here we we saw this already. We should not be shocked. We are going to use nickel. We're going to hydrogenate this by pumping in some gas with nickel on the bottom of the vessel, and we see double bonds here, and we can count this up. They tell us it's palmolitic, so this would have been palmitoleic acid, which is we got 1, 2, 1, 8, 9, 10, 15, 16. So 16 carbons. So it's not palmitic acid, which is 16 carbons, but when it has a double bond in it, it's palmitoleic acid. So very close in name. Once you work with these, you start to get you really need to work with them rather than just listen to me. Listening to me is a good starter, but now if you really want to learn this, you need to go a little bit deeper. And so the 16 carbon unsaturated chain, it's a molecule. We're not going to break the bond here where the ester is. We're just going to add hydrogens across this, and it's going to become more single bond. It's going to definitely become more saturated. And so what do we get? Well, we're going to probably change the name of the molecule in the process. Well, we got rid of all the double bonds. So this is going to become palmitic. The oleic is going to be gone. It's going to be called palmitic. You're going to lose this end part of the name. And so the double bonds are gone. So this is probably going to raise the melting point, right? It's going to be more solid at room temperature. And that's the result of hydrogenation. It's good to have index cards that teach you this stuff in general. Maybe you'll be taking a pharmacy test, a nursing test, a medical college aptitude test. Maybe some of you will decide to be doctors. I'm sure some of you are smart enough to do that. But now we're getting into something different. Be careful of the reagents when you're looking at stuff like this. What are the reagents involved? Okay, water is one of the reactants, and we got 3 of them, and we got H plus acid, or we use an enzyme. Remember, the neat thing about chemistry is now we're getting to the point in society where the scientists and technicians know how to get enzymes and use them in vitro in a test tube to do the work that acids or other things used to do. Of course, enzymes are very sensitive to the pH, so the acid still might be important for the enzyme's function, but you might be able to get an enzyme that can do it way faster than what you could normally do in a lab because the enzyme sometimes can make gazillion molecules over so much time. We don't know. We have to compare 2 methods. In vitro means in a lab, basically non-living materials. In vivo would mean in a living system. You'll learn that in biology. And so we could use water to lyse this. We can use water to break this bond. Water to break this bond. Water can attack it. The oxygen can attack the carbonyls here. The acid can protonate this. I won't go through the mechanism because we really just want to see what the result is. We reformed the glycerol molecule we started with previously in our previous learning about how fats are made and how glycerols and fatty acids react to form lipids. And then we have this reaction where we also protonate this carboxylic acid when we're in acid media, and we get 3 palmitic acid molecules, right? So we went from tripalmitate to palmitic acid. Because we protonate this, we have our full carboxylic acids back. So triglycerols can be split into glycerol and 3 fatty acids using a strong acid like HCl or sulfuric acid, or even digestive enzymes, which are called lipases, because they act on lipids. Now this is a lipid. These are not lipids. This is a fatty acid and a glycerol molecule. Let me repeat that. This here is a lipid. It is a fat. But when we break this up, we get fatty acid molecules and glycerols. This is not a lipid. They make up lipids, but in itself, they're not really a lipid. So be careful about what the definitions are. I see people with different ideas, and they need to make sure it's the official idea. So saponification and soap. So you can take these lipids and fats, and you can use sodium hydroxide to break up these fats, and you can create soaps. The Some of you are too young to probably watch this movie yet. I would say you should be 26 before you watch it. But Fight Club, they made soap. And so they would take fats from animals or even people for goodness sakes, just it was a science fiction film. You don't want to do this in real life. They took fats from like a liposuction clinic, so it wasn't anything horror film like. They just kind of took things that were already being thrown out and they made soap from it. It was a crazy idea. It has all sorts of social, economic, gender issues going on there. It's a very interesting movie for those involved in politics or just wanting to think about society in general. But you could take fats, these lipids, and you can hydrolyze them with strong base in the presence of heat, and you can get a soap. Um, Sodium hydroxide is great for making the solid soaps that we have as bar soap. If we use potassium hydroxide instead of sodium hydroxide to basically saponificate those lipids, we would get a softer, more liquid-like soap. And so we know a little bit now about soap making, and we split this triacylglycerol into glycerol and the 3 sodium salts of fatty acid or whatever is attached, right? So just to we're doing it again. We're not using water and acid or water and acid and lipase. We are just using sodium hydroxide and heat, and and the hydroxide is base, and it's going to come over here and attack these carbonyls. It's going to attack these carbonyls. It's going to attack these carbonyls, and we can end up breaking this molecule. We break the ester bond. We reform the glycerol, the trihydroxy alcohol, and then we make this palmitate, which is a carboxylate. Palmitate is a carboxylate, and it has negative charges, and it will associate in the liquid, or it may precipitate out, which it will, right? It's not going to float. This is not going to float around in the liquid unless it's at the top as a whole different layer. You're going to get a separation in the water, and it's not going to be able to dissolve very well in water, but it can dissolve in water because of the fact here of this negative charge and this sodium and positive and negative charge. So you have really an amphoteric molecule. Part of it is fatty-like and oil-like, and part of it likes water. So this head here will like water, and that's why soaps are so useful, because they can dissolve grease in clothes, but then they can interact with water and be driven off the clothes into water. So soaps are very interesting molecules. Part of them is insoluble, part of them are not soluble. So you see the chemistry here. Strong base, some heat, and you're making soap, which is the movie Fight Club that I mentioned. Again, you should be 26 before you see that movie, in my humble opinion. Okay, so organic and lipid reactions. Okay, so we have 4 types of reactions that we've kind of talked about for these lipid molecules made out of fatty acid and glycerol, or the reactants that make up the products. So we can do esterification, we can do hydrogenation, hydrolysis, and saponification. So let's just look at this again very briefly. It's carboxylic acids or fatty acids react with alcohol or a glycerol, and then you have heat or acid, or you can use an enzyme in the human body and you create an ester or a triacylglycerol with 3 esters, and then you have a dehydration reaction where water is formed from the reaction. Hydrogenation, we've seen that. H2 gas reacting with a double bond in platinum and forming an alkane. It's the same thing when we think about lipids reacting. The unsaturated fat, which is a triacylglycerol with the double bond in its fatty acids. You can add the hydrogen and nickel, and you get a saturated fat where the double bond is turned into a single bond. It goes from an alkene to an alkane on the fatty acid. We've seen that. We've seen all this chemistry. Hydrolysis, we're connecting everything together towards the end of this class, and you should be really appreciative of all the learning you've done. So we take ester and we react it with water, and water can attack that ester at the carbonyl with a little bit of acid and heat. We can break it up into the carboxylic acid and the alcohol. We saw that, but now we've learned triacylglycerols, which are fat molecules, lipids, right? Lipids are fat molecules that have ester groups from the triacyl alcohol, just like we saw earlier with just a plain old ester. We didn't think about its biological implications. Now we're thinking about how this chemistry applies to biology and biological systems and molecules found in biological systems like us human beings. So triglycerol fat is reacted with 3 water molecules and an enzyme, and it can break apart that into 3 fatty acids and glycerol for metabolic reasons. It might have a reason the body wants to do that, to get the unstored energy, right? We saw the polar bear from hibernation in a previous video. Saponification, what is that? It's taking an ester with sodium hydroxide, and we didn't call it saponification then. Well, yeah, we did. And then we add some heat and we break up that ester for the carboxylic acid and we get the alcohol back. But we can do that with a lipid molecule, which is a triacylglycerol molecule. We react it with 3 sodium hydroxide units and we add some heat and we get 3 sodium salts, a fatty acid or a soap, and you get the glycerol molecule back. So these are lipid reactions, really cool stuff. And moving forward, what happens here? You should know now. You should know. This should be easy for all of you. Hopefully, you look and you see this lipid molecule, this glycerol trilaurate, which is from lauric acid. All right, lauric acid is 12 carbons. It's completely saturated. We see 3 H2O molecules, so we don't see any double bonds. So we're probably going to break this ester up. We're going to add this lipase. The enzyme is going to do the work for us, and that's going to make our life easier by using enzymatic chemistry. You're going to learn more about this. Is becoming more prevalent in biological chemistry as society progresses in its knowledge and organization and useful knowledge. You have to have, of course, a civilized way to disperse the knowledge. These are all political things. But let's get back to chemistry. We're able to break this apart, and water molecules can break this apart, reforming glycerol with 3 lauric acid molecules. And we are able to break the ester bond, break apart this lipid. And when it's a lipid, it can be used as a membrane, maybe. And maybe there has to be some doctoring up of this. But when we break it apart, it may end up getting returned back to the metabolic processes. Maybe it needs to break up fats for energy. These fatty acids get broke up for energy, and the glycerol gets turned into an amino acid. That's the glorious nature of all these metabolic processes in the human body. It gets sophisticated and complicated, but it's also simple and complicated coming together. So a glycerol trilaurate becomes 3 lauric acid molecules, and the glycerol backbone is recovered in that reaction. Thank you so much. Hope you're learning lots of chemistry. This has been GOBC. I'll be back with more, and enjoy your learning in the whole process. Thank you.